All right, hello everyone.
Hello.
My name is Franz, and this is Leo Zaprunis. We're both core developers for the Sktime open source package. And today's PyData London tutorial for Sktime will be about how to write your own estimator. So the notebooks for the tutorial, they have been posted on the Slack channel. You can also find a link here on the screen. And if you have any questions, then helpful core developers of Sktime will also be monitoring the PyData tutorials channel. So including Leonidas will be switching throughout the presentation. And if you have any questions about the tutorial or how to run the notebooks, just post them there. And what we are going to do today is going through the process of writing your own estimator. Sktime is a unified framework for machine learning with time series. It's Scikit-Learn-like. It's meant to be compatible with Scikit-Learn in the PyData ecosystem. And one of the properties that it shares with Scikit-Learn is easy extensibility. So it's easy for you to write your own estimators that are compatible with Sktime. Even in a closed source situation, for instance, if you're not able to share your code, you can still write it in a compatible interface and leverage the entire framework, the plumbing that Sktime provides for you. We are going to follow today the developer guide on how to write your own estimator. You can also find a link here. If you haven't heard of Sktime, there will be a 10-minute introduction first before we go into the specifics of implementing your own estimator. And you can also find videotape tutorials of generic Sktime use if you haven't seen it from the PyData Global 2021 tutorial, and another tutorial you might like to check out is the one on probabilistic and hierarchical forecasting. All right, questions you can ask in the Slack channel. We'll have opportunities for questions at the end as well. Let's get started. So, quick introduction, what is Sktime? As I've already said, it's a Scikit-Learn-like toolbox for learning with time series. It's open source permissive license Python. It's also openly governed, but we're NumFOCUS affiliated. We're trying to aim for an equal split between academia, industry, and early career contributors. We currently have 19 core developers and a community council that governs Sktime and integrates with NumFOCUS. Everyone can join Sktime. You can contribute if you want to become a contributor or a community leader. Everyone is welcome. You can join our Slack or Discord. Slack for developer discussion, Discord for events. The regular community collaboration sessions on Fridays, they're online on Discord. So today is a Friday. You could, for instance, join the late session. The schedule is all on Slack when you log in. We also have a developer sprint here in London, July 11 to July 15. So it's London plus virtual. You can register online by following this link on Eventbrite. There is also job opportunities on the horizon, which I wanted to mention. So watch the job channel. We have a mentoring program for which you can apply on a rolling basis to start your open source contribution journey. So, Scikit-Learn. What does a Scikit-Learn-like toolbox mean? So let's first look into Scikit-Learn if you haven't seen it, and by that we also are going to look into what it means for Sktime to be Scikit-Learn-like. So Scikit-Learn-like toolboxes provide a unified API and workflows following the object-oriented strategy pattern. The composable allow model building in a modular fashion, and importantly are also open, extensible, and contributable. Important for today's presentation, extensibility, so it means it's easy to write your own components that are compliant with the general interoperable package interface. The components that you write, which are interface compliant, they can be possibly closed source, closed license, but they still interoperate with the general package. And the package, so Scikit-Learn or Sktime in this case, both provide testing utilities which allow you to check validity of your custom estimator. So unified API. You might have already seen it if you're using Scikit-Learn, right? You specify your data, you fit, predict, evaluate, and the unified interface here means that, right, step 3, fit, predict, evaluate, is all the same for all estimators of the same type. For instance, the random forest regressor, you could have chosen a linear regression model here as well. and everything else would be the same. Modular model building, pipelining, you will have also seen probably the Scikit-Learn pipeline interface, so you can pipeline a so-called transformer, here the standard scaler, which normalizes your data, and a regressor to form a pipeline, which then also behaves as per the unified interface with fit and predict. It exposes the same methods and the same signature for use. So in Scikit-Learn, of course, the learning task is learning tasks related to tabular data, so supervised regression classification or the unsupervised clustering and dimension reduction tasks. There's a common estimator API, and the estimator API is the mirror-specific learning tasks. Now, for time series, what Sklearn does for tabular learning tasks, Sktime does that for time series, and there are a number of challenges for time series. So number one, multiple data formats. So you have already on the conceptual level, you have univariate time series, so time series observations over time on one variable. You have multivariate data, so repeat observation of multiple variables of the same object over time. You have panel data, that's a collection of time series, so you have multiple objects that you're observing, and you have repeated observations of these multiple objects in your panel, so objects or experimental units, collections of time series, and also more. You have learning tasks that also vary quite substantially. So forecasting, given the past of a time series, you want to predict its future. You have time series classification, so your time series are your different observations that you want to label as a whole into one class or another. Time series annotations, so given a time series you want to annotate, for instance, here's a change point, or these are the segments, and so on. Even within those learning tasks, we have variations. So I have trying to forecast a single time series or multiple in a panel. We have a hierarchy of time series and so on. There is a relation between these tasks, which is also important. So what we're trying to leverage in Sktime is also the connection between the tasks, trying to solve one task with a solution for another task. A very common example, so here is a lot of tasks in a table. You can also read more about it in the Sktime research paper that is on the archive. But one very popular step of solving task A with a solution for task B is a reduction approach to forecasting. So forecasting, remember, trying to predict the future of a time series from its past. Supervised regression being trying to predict y from x, as in Scikit-Learn. These are not the same tasks, but you can solve forecasting by a supervised regressor by running a sliding window and tabulating in a certain way. And then you fit your estimator to the tabulated xy, as you see here in the bottom left. And you can apply it in predict for forecast if you apply the so-fitted regressor to the final window of your time series that you want to forecast. So that's an act of reduction, and it's not the same task. What you want to have in a clean interface is to expose this act as an algorithmic wrapper or a composition act. And you want also to be able to tune, for instance, things like the window length or the step size in this, and Sktime also allows you to expose this as a compositor, just like the pipeline object in Scikit-Learn, and tune over the parameters of this composition, or more specifically in this case, the reduction step, like the choices from... Sorry? There's an audience question, yes?
The standard function analysis armor, moving averages, definite.
I can't. So okay. So the question is, are there also standard approaches in Sktime? Of course, they are. You have autoregressive models, ARMA, ARIMA as well in Sktime, and they follow the same interface, right? So one of the challenges here would be, okay, if you do this in Scikit-Learn, it has a completely different interface, for instance, from stats models ARMA or ARIMA, whereas in Scikit-Learn, in Sktime, this is all brought to the same interface. So you wrap a Scikit-Learn regressor in your reduction strategy, and it has precisely the same interface as the ARIMA model that we interface from stats models, which of course is also a baseline choice that you want to try if you forecast. Coming to the end of this, with Sktime, we want to create a unified framework, both ecosystem-wise as well as software-wise. There's multiple learning tasks here, and we try to provide a unified interface, software interface, for the multiple learning tasks for each learning tasks. So if two algorithms do the same thing, for instance, ARIMA and the reduction strategy using a supervised regressor, they should follow the same base class interface. And there's more, of course, than the software side to it. Sktime is also a community for research, right? We're connected with academic centers, for instance, on forecasting, on time series classification. It is a community, so we have workshops and community engagements like this. Everyone can become a contributor and a community member or a community leader. And we're also trying to build educational materials such as this tutorial, which will be videotaped and go on YouTube alongside the other tutorials that we have videotaped. All right, that's the intro to Sktime. So I hand over then to my colleague Leonidas for the first half of the implementing your own estimator. And if you have any questions, Slack, I'll be there, and I'll wait for developers to answer them.
Thanks, Franz. So yeah, we'll start with the basic way to implement your own Sktime estimator using the extension templates. We'll consider this workshop successful if by the end of it you can implement your own estimators, use it with confidence in your projects. And to get there, first we'll start with a basic developer setup with Jupyter notebooks and an IDE. We'll use VS Code, but anyone can use whatever they like. I'll introduce the Sktime interfaces, the public side, so what the user uses, and the private extension interface. And then we'll go through the basic steps to implement Sktime estimators. We'll do a simple Sktime transformer, a simple Sktime forecaster, and then we'll also look at the testing utilities and some debugging as well. And after this section, then I'll hand over back to Franz for the more advanced extension stuff. So, developer setup. In Sktime, we have a developer guide that includes very useful information like installation, the dev installation, Git and GitHub workflows, coding standards like Flake 8, and all that nice stuff, how to implement your own estimator, which is what we're going to do today, and various other things. This is very useful if you want to start contributing to the project, and this is also what I followed when I did my first pull request, so I think it was a very smooth experience. And yeah, as I said, for this workshop, we'll jump back and forth between Visual Studio Code and Jupyter Notebooks. In case you haven't done that already, it's 9 a.m., so it's justified. If you want to follow along, you can clone the repo. The link is in the Slack channel. And then for the installation, you have various different options. You can just install the requirements, pip install -r requirements to text. We recommend you use a virtual environment to keep your dependencies at bay. So you can either use Python virtual environment or Conda. And I always forget this step, but it's very useful if you want to use notebooks, make them available in a separate kernel as well. So here, for example, we can change the kernel to PyData Sktime, and life is good. So, Sktime. What is the public user interface and what is the private implementer interface? This is the core idea behind the extension templates and why it's easy to write your own Sktime estimators. Sktime estimators have those two key interfaces, the public and the private. So the public interface has the classic steps that Franz showed in the intro, so fit and predict. Those are the same for all estimators that take care of the same learning task. So for forecasters, it will be fit and predict. For transformers, it will be fit and transform. And the contract, so the public interface, is shown and documented in the base class for every learning task. So, for example, the base forecaster. The private interface that the extender, so us in this case, will use is denoted by an underscore, so the classic Python convention of private or protected methods. And it's the same as with the public interface for all estimators of the same type. And the contract for this is documented in the extension templates, which are available in GitHub, and we'll go through them today as well. You might be wondering, okay, why do we have those two interfaces? Why can't we just say, okay, we have fit, I have to implement fit, why there's this weird underscore fit? So the main reason is there is a bunch of layers that you have to go through every time you fit an estimator. And if we didn't have this approach of the private and the public interfaces, you would just have to copy-paste them, and it would be really difficult and annoying to copy-paste the same things every time you want to implement a new estimator. Those can be check the inputs, coerce to the right type because multiple types are supported, convert to this and that, or if something works only on univariate and it automatically works in panel data as well because of the vectorization backend. This is a very nice schematic of the amazing stuff that's happening between the public and the private interface. There's dragons, good dragons. There's a bunch of different stuff that we'll see as we go through the tutorial that you just don't have to worry about. So let's have a look at the public user interface. If this is not your first time with Sktime and time series, you will probably have seen this. So we're loading a very popular time series dataset, which is the Australia flights, passengers, or something like that. And we're using a naive forecasting algorithm to predict it. So this naive forecasting algorithm will say that what happened last year will happen this year. The forecasting horizon is an important object for forecasting with Sktime. It has different shapes and forms, but you can fundamentally use a list of integers, and those are the steps you would like to forecast ahead. So we've defined our forecaster, fit on the time series, predict on the forecasting horizon. You might notice that the forecasting horizon is added on the fit step. Sometimes some estimators require this. Otherwise, you can just add it on the predict step, and we'll go through that again later on. And what you see here is that the public interface to get a forecast is just 3 lines of work. And that's the same for all forecasting algorithms in Sktime. If we look at the docs for the base forecaster and the public interface contract, I'm not going to go to the GitHub, but if the link is here for you if you want to do that. Basically, the forecasters have to do fundamentally 3 things. They can fit on time series data, they predict the future, and you can update them, which is adding some more data and then update using that instead of refitting. And then there's also some convenience methods like fit and forecast, update and forecast, and so on. Here's how our naive forecast looks like. It doesn't look that bad to me. Not sure why we call it naive, but yeah, nice and easy. So what happens if you want to implement your own forecasting algorithm? So you want to do better than naive or whatever is out there in Sktime or other packages. So in Sktime, we have private methods, as we said, that in the extension template, you just need to fill in. So let's have a look at one of the extension templates for forecasting. Here we go. So we differentiate between extension templates. We have simple extension templates where you just have to implement the bare minimum. In this case, it would be fit and predict. And we also have advanced extension templates where you have to implement more fancy stuff like update, predict, intervals, and so on. So if you read through the docs, it basically tells you what you need to do. So you just have to go in, change the names, write the doc strings, change these tags. We'll go through the tags in more detail later. Yeah. Here we go. Thanks, Franz. So there's also to-dos on what you need to do as comments in the code. When you do that, feel free to remove them because the code would look ugly. And there's explanations about what everything does. So here, for example, for the init, you need to add any hyperparameters and components to the constructor. So if we would implement a naive forecasting algorithm that's a seasonal naive forecasting algorithm, we would need to add the seasonality, for example. And then the next thing to do is to implement the fit logic in the private fit method. You will never touch the public fit in this template, which is very nice. Same for predict. And finally, if you want to use the testing framework that we'll see later, you can implement the get test parameters that creates the various test parameters that you can use. So we saw what we need to implement and where. So if you want to implement something, you just copy paste that extension template into your code, into your package. You have Sktime installed, you can start. What happens between fit and private fit? So we can look and examine the plumbing layer using the excellent debugging utility Make Mock Estimator, made by one of Sktime's most illustrious contributors, me. So Make Mock Estimator is a new utility we introduced. It's a testing/debugging utility that adds logging to internal methods calls, and it also shows you what the inputs to these methods were. I think it can work with any Python class, so you can test that for yourselves. So we make a mock estimator based on the naive forecaster. So now we can see what happened when we called fit. So what happens is, first you call fit, and then a bunch of other stuff happens, and finally the method you implemented is called. So what are these methods? So first, it's the fit you called. Then after you call fit, we reset the state, so start clean, get the parameters of the estimator, check the forecasting horizon and coerce it to the right type. So before we had a list, but on the backend this will become a forecasting horizon object. Get the tags that we saw, so those are useful information about the logic of the plumbing layer. Check the inputs, set the cutoff, which is the most recent time point in the training data, and then finally, use the private fit that we have implemented. So, you can see, for example, and we'll see that in more detail later on, that there's a lot of data types conversions that happen between the public interface and the private interface. And again, that's stuff that you don't have to worry about. Same for predict. So when you call predict, there's a bunch of stuff happening. So first, you have to check that the algorithm is fitted, otherwise we throw an error. Check the forecasting horizon, get the tags, check the inputs, and finally predict. So, to summarize what we've learned so far, Sktime estimators have two key interfaces: a public user interface, fit predict, a plumbing layer between to avoid copy-pasting code, boilerplate errors, all that jazz, and a private user interface, _fit and _predict. As an extender of Sktime, you just need to implement the content in the private user interfaces and set the correct tags and arguments in fit and predict to appear in the favorite format. So, now we'll go through implementing our first estimator. So, here is a link to the extension templates that you can copy-paste from GitHub. At the high level, the steps are: identify what you want to do. You want to make a transformer, a forecaster, classifier. Copy the extension template, complete the extension template, run the test suite, and then keep going until the tests pass. And we'll go through the test suite in detail a bit later on. So, for the first example, we'll implement a min-max scalar transformer. We'll use the transformer templates to implement the min-max scalar. And here is what it looks like. So, you can notice that the number of airline passengers is now bounded by 0 and 1, which is what our min-max scalar transformer should be doing. And we can also inverse transform it back to what it was. There's also, for those of you who are not, who are a bit suspicious, an assert statement that makes sure we're okay. So let's have a look at the transformer extension template, and then we'll try to fill it in. And here we go. So let's have a look. So first, it's recommended to write a docstring, so we'll do that. Fill in any parameters once those are finalized. We'll need to check the tags. So what is the scientific type of the time series, or sci type as we say it in Sktime, that our transformer is supposed to work with? Is it series, a panel, multivariates? What's the output of our transformers? Does it return back a series? Does it return a panel, something else? And various other different tabs. What's very important here is the inner M types. So what the inner M types are, and again, Franz will go through this in great detail on the next part, are guarantees about what type will reach the private method. So, for example, you can use a pandas data frame for a univariate time series, but you can also use a pandas series, or maybe something else. NumPy array. What the inner M type guarantees is that when that series reaches your private method, it will be the specified type in this tag. So you can start with a NumPy array as your inputs, and then it will turn into a pandas data frame, so you only have to worry about pandas data frames. So we'll just copy-paste this extension template. I'm not going to do it live, too risky, with my luck. And we'll implement the private fit and the private transform, and maybe the inverse transform as well, to do the min-max scaling. Yes?
Good question. If you're inputting NumPy arrays, how do you infer timestamps later on, or is that not possible?
Good question. So there is an integer index that is supported. And what?
Always interpreted as a range index.
Yeah. So it's always interpreted as an integer. It's not like it's not time, but you know it's still a sequence with that's ordinary. But yeah, that was a good question. So let's look at the simple transformer. Imagine that we copy-pasted the extension template, changed the name. Instead of my transformer, it's now min-max scalar. Say what it needs to do. So the min-max scalar applies the transformation that ensures that the series is bounded by 0 and 1. Could do better with this docstring, but it's okay. So our site type input is going to be series. We're going to output series. So it's going through the tags. It is an instance-wise transformer, so it works on a series-by-series basis. It has the capability of inverse transforming. It works only on univariate time series. And you can see that I've changed the inner M type to be a panda series, just because I'd like to work with panda series for this one. So I'll skip through the rest and go straight to init. So a min-max scalar doesn't have any hyperparameters, so we just go like this. And here's the private fit that we made. So as part of the private fit, it's nice to change the docstring to say that, okay, the X in this transformer is guaranteed to be a panda series. So it's useful for developers who will see the private interface at some point to know that. And Y is ignored. It's just here for interface compatibility with other transformers that might need Y. So in the private fit, we just save the min and the max of the input data, and then that's it. So the next step is to implement the transform, the private transform. So again, same thing. Change the docstrings to what's expected, and then some saving of attributes of the transformed X and Y. Those are not used, but it's just, I guess, nice to have them there. And then transform your X with the logic that the min-max scalar likes. So X minus the minimum divided by the maximum minus the minimum, and then just return the transformed X. The inverse transform is also implemented in this one. You don't have to implement it, but we implemented this for this example. So it's just multiply the transformed data by max minus min, and then add the min. And also, because we'd like to use this in the testing framework, we return an empty dictionary, which means just use the default parameters for the tests. So we've seen what we implemented, and now it's time to check that our transformer. Oh, that's strange. We might need to rerun this. Let's see.
This live demo is, of course, completely intentional.
Yeah, all that is intentional. We are rerunning it. It's really fast because Sktime is great. It's okay. It's under control.
I can do some stand-up comedy.
Go ahead, Franz. You need to be fast because we fixed it. Okay, no stand-up comedy needed.
My arms are tired.
So, sorry about that. We tricked you. We implemented a buggy transformer just to make it fail on the test framework. So, yeah. So we have a test framework. There is a tech estimator utility function, I think developed by Franz, which is a very nice function for and Marcus, which is a great tool for the extenders to make sure that the new estimator is going to be compatible with the Sktime API. So you just need to import it from Sktime. So from Sktime utils estimator checks, import check estimator, and when you run it, the results will be stored in a dictionary. And you can also print or raise the exceptions. If you say return exceptions true, then it will print exceptions, not raise them. So we see here that our estimator has failed. And we can see where, right? So it failed on the test. Test methods do not change state. Min, max, scalar transformer, fit transform, series, univariate transform. So we can get more details about this if we just look at the dictionary. Here we just print it in a workshop-friendly way. So the error message is the min, max, scalar changes dict, so it changes the state during the transform step. The reason location of the discrepancy is it has those new keys, x transformed x min, transformed x min and transformed x max. So a requirement from Sktime is that transform, predict, and that stuff do not change the state. And that's key to prevent leakage and other horrible stuff. So the methods that typically change state are fit, update, and so on. So we can fix that, luckily. We know exactly what the problem is. So here, in the new transform step, we will just not do that. Those were useless anyway. So then, if we rerun the testing framework, all tests are passing, and we're confident that our new transformer is compatible with the API in all ways. So now let's look at the simple moving average. Yeah, go ahead.
Just a question about the API. So when you speak about states, when you fit, so yeah, fitted attributes. So I think that in Scikit-Learn, basically, yeah, fitted attribute that finish gives an underscore. So do you have the same thing here, or because I see that you use set dot underscore mean and not mean underscore? I mean, do you have like what is the API basically for?
Yes, you're right. So there's that might be a mistake on my side. You're saying that fitted parameters are denoted by the name of the attribute and an underscore on the right instead. Yes. So I think that's correct.
It's weakly enforced, so that
Yeah.
tests won't catch it. Maybe we should write some tests for it.
Good stuff.
So we recommend, I think, implementers to adhere to that with the underscore at the end, but the tests currently don't adhere for it.
So feel free to make a pull request. Yeah, so for a simple forecasting algorithm, we chose to implement a simple moving average. People call this simple moving average because a real moving average is not that simple. So what a simple moving average does is you ask it to give you a forecast that is simply the mean of the last 5 observations. And here is how it looks like. So we say use the last 5 observations on our lovely airplane passengers dataset to predict the next 3 steps. Okay, so to do that, again, we just copy-paste the simple forecasting extension template. And then imagine that this is copy-pasted. We then implement what the to-dos are there. So for the simple moving average, we'll write a docstring. The simple moving average has one parameter, which is how many of the most recent past observations will you use for the mean. So that's window length in our case. We will change the tags to meaningful tags for this estimator. So it's going to work on univariate time series. It ignores exogenous variables. So it doesn't use, for example, inflation, future inflation for predicting airplane passengers. So that's what exogenous variables are. It doesn't handle missing data. The inner type for the time series is a series. It does not require the forecasting horizon on the fit step. Some algorithms will. For example, Franz talked earlier about using machine learning for time series using the reducing strategy. So if you do that, you can, for example, fit a new random forest regressor for every time step you want to predict in the future. So the algorithm would need to know how many time steps you want to predict in the future in advance, because otherwise it can't fit a different one for every time step. And it can't predict intervals because it's simple. So again, here's the logic. We will give a warning that y has less time steps than the window length, and the full series will be used if that's the case. And otherwise, we just take the mean of the most recent observations up until the window length, and then don't highlight this again, but I did the same mistake, storing it in this format. So we store that forecast value. It's going to be the same for all the steps. And when we predict, we need to just make the index of the output series. So just the index is the forecasting horizon to absolute, so the absolute dates, not relative to the cutoff, and just return the same value for all the dates. We will also implement a few different testing parameters of different window lengths just to cover everything, all the edge cases. And then finally, once we do that, we will go to the testing framework to check if everything works. And in this case, there's no bugs, so all the tests pass, and we can go on using that wherever we want, compatible with the Sktime API. So, some credits. Me and Franz created this notebook. The extension templates were created by Franz, and the extension guide. The base class is a group effort by Marcus. I don't know Big O's first name.
He doesn't want this to be disclosed.
So Big O. Franz, Svea, and Mirai. Transformers base class. Yeah, and a lot of other people.
If we forgot anyone, we will make a pull request.
They'll be angry at me later.
I will just update this.
And now, back to Franz for the advanced section of this workshop.
All right. And Leonidas will answer all your questions on Slack. Yes. All right. So, notebook number 3. Okay. So we've seen how to use the simple forecaster and transformer extension templates, and I now just wanted to show some advanced patterns that might arise, for instance, if you want to implement probabilistic forecasters or transformers, forecasters for hierarchical data, or composite estimators such as pipelines, so estimators which have other estimators inside. Another example would be the reduction estimator that wraps an Scikit-Learn estimator, for instance. And we'll also look into automated testing, so how you can integrate with your test suite. All right. So 3 examples in this notebook. All right. So update and probabilistic functionality in the forecaster first. So how to use the full extension template. All right, so we'll look in a moment at the extension template. The thing, again, to remember from the basic notebook is we have the public interface, the public user interface, the private extender interface. The extender interface is the one against you implement, the contract of which you need to fulfill if you implement your estimator. And the public methods will have, in this case, will be update and predict underscore interval, quantiles, and so on. So Sktime forecasters currently have 4 public interface points for probabilistic predictions, including interval or full distributional predictions. There's 1 interface point for updating, say in a stream and online setting, and the general picture is the same. To the public side methods, you can pass a number of different data formats, whereas in the inner methods, you can assume specific data formats that, that you will see there and use in your implementation. Similarly, right to the public interfaces, you can pass things like alpha or coverage for the interval quantile forecasts as numbers or lists in the interface. In the inner interface, this is always guaranteed to be a list, for instance. So the inner interface is typically easier to implement against, and checks have already been done, conversions have already been done. So maybe one also minor thing specifically about the advanced forecasting interface. There's also defaulting happening here. So there's default behavior implemented. If you implement one of the 4 probabilistic forecasting methods, then usually, depending on the method itself, of course, right, the others or some others might automatically be implemented. For instance, if you know how to make quantile predictions, then mathematically you also know how to make interval predictions, and you need to implement only one of the 2, and the others 2 become implemented through assumption of a normal distribution, which may or may not always be accurate. But you get this as default behavior. So let's look into the advanced forecasting extension template. And at the top, you have more things listed. So this is similar. It follows the pattern of the simple forecasting extension template. All extension templates look similar. But of course, you also have a list of other methods that you could be implementing. And what we're going to do is we're going to implement all the optionals and see what happens. So we're going to implement the underscore update. So we're going to make a non-trivial online or stream update. We're going to implement one of the interval predictions in a silly fashion. And we're also going to implement get fitted params. So that's similar to get params. So getting the hyperparameters, but in this case, it returns the fitted parameters as a dictionary. All right, so let's see what we need to implement. Now, right, there's the tags. Maybe we remember, okay, always look first at the tags. Is there anything we need to change? Maybe there's nothing we need to change. Maybe there's something we need to change. I do not know, but we might see later that hopefully the test will tell us if we forgot something there. Fit and predict we have already implemented. So what we could do now, of course, we take the estimator we've already implemented and then copy over just the methods we additionally want to implement, or we can start over with the full extension template and copy over the parts from the estimator we have already implemented, usually copying the parts from the extension template into an existing forecaster if you want to implement more methods is safer. All right. So update. Here we need to implement. Here is the generic guarantees. So of course we want to change this to y is a pandas series in the final doc string. All right, so these are so update predict single. It's a default implementation. We don't need to worry about that. So predict quantiles is the function, is the private method for quantile predictions, and here we see, okay, we get FH and X, so what we also see in predict, forecasting horizon optionally, and an exogenous data, which we'll ignore in this case. The important input is the alpha, so the list of quantile points at which we want to have the forecasts. The return needs to be a pandas data frame in a specific format with a multi-index, right? So the column has a multi-index which has possibly variable names, and the second level has the values of alpha being passed. The entries are the quantile forecast, the rows are the absolute indices where we make a forecast at. So predict interval We don't need to implement this because in base class this has a default implementation. So if we would now copy this over, if we would now copy predict interval over but don't fill it in, then the estimator would break and the tests would tell us, but of course we're not going to do that. That's also a popular bug. And finally, we have get fitted params. That needs to return a fitted parameter dictionary that does not have at the moment this public-private split, but there is still one element of boilerplate which we need to watch out for. I'm not going to tell you at the moment what it is because the tests are going to tell us in a moment. So this is the full extension template for forecasters, and now let's pretend we start filling it in. So what we're going to, in the final thing, of course, you want to change the doc strings and all to that of your forecaster, but for the purpose of this tutorial, we left them in so you can see, you can compare the to-dos to what is actually written there. All right, so we want update and proba and also get fitted params. And we fill in here the update. So it's update of a moving average with a fixed lookback, and I started to implement it, and I noticed it's well, a bit more complicated than you would think because there is 3 different cases depending on the length of the new update data and the full data. So the window could be smaller or longer than either of these windows, which gives you 3 cases that you need to take care of. But each case is really a simple arithmetic formula. And as said, just to make all Scikit-Learn developers here angry in this audience, the underscore is at the front. Now, for predict quantiles, we've done something very silly. So all the quantiles are just the same number, which means the estimator is absolutely certain that the prediction will be the point prediction, which is maybe not a good thing to do, but for the purpose of this tutorial, to do something illustrative, what we have to do is just get the data in the right format. So create a multi-index, the multi-index that is supposed to be returned here. So it's univariate. We can use the, we should actually be using the fill-in capital letters quantiles, and the second level in the columns is the alpha at which we predict. And that also automatically will then, by defaulting, fill in the predict interval and the predict variance method and all. And for get fitted params, we return one parameter called forecast value, and we read out the fitted param here. So that will also return a dictionary. Okay, so far so good. The test params we can actually leave the same because in the tests these still cover the different cases of, okay, is the window now larger or not than, say, the update batch or the full batch. All right, so now let's see what happens. And okay, this is importing from a module that's called buggy, so you might expect some things to happen. And so we have 3 test cases, so 3 test estimators coming from the 3 parameter sets, and they all come back with a failed test, so 2 failed tests each, test pred in tag and test raises not fitted error. Now in order, so you can look at, of course, the error message of each, and sometimes this is helpful, sometimes it is unspecific. So the first test, if you look at the results, remember this is a dictionary returned by the utility check estimator. Right, we look at the results there. The key is simply the PyTest string, so test name and fixture combination in square brackets. We look at it and it says, okay, it does implement probabilistic forecasting. Oh, but we forgot to set the flag capability pred int in the tags. So the implementation is actually inconsistent with how we set the tags. So what we need to do to make this go away is to set this to true. So also in terms of the tag interface, we have this correctly set in accordance with the implementation, namely that we have actually a predict interval and a predict quantiles function that has meaningful content. The second one gives this. So it gives an attribute error. So the exception itself is not too useful to look at. It says, okay, we're trying to access an attribute here, namely the forecast value, and that's a bit strange. So that's not very clear. Now, what we can do is look at the traceback and test. So now we need to find out, well, what does the test actually test? I think it's a good example. Now, of course, what we could do in the next month is to make this specific error message clear, and we always appreciate pull requests or reports if you think the error message is not clear. But I picked this as an example because there's a lot of tests running, and not all of them have really clear error messages. And invariably, at some point, you might encounter, if you run check estimator, an error message that is not very clear. So what you can do in that case to find out what's wrong here, usually you need to look at the traceback as well as the test. So if we now go into the test, so that means searching for test traces not fitted error, either on, say, via the GitHub web interface of the Sktime repository, or if you have a local clone of it, you can search in the in your developer IDE. Or what you could also do, if you really don't know what it's about, you just go onto the developer Slack and in the contributors channel ask, okay, I test my estimator and I get this weird error, can you help me? Or you go to one of the community collaboration sessions, and usually some helpful developers will be there, and you can screen share and you can drill down into the problem. Now in this case, the traceback of the test is useful. Of course, you can run it with the PyTest if you have the full developer set up, you have a local clone, and you have PyTest running. But you can also get it from check estimator, because as Leonidas has previously said, right, if you switch this return exceptions flag to false, so instead of returning it in returning the exceptions in the dictionary, it's going to raise them, the first one it encounters. And you can also subset the tests or the fixtures by the arguments tests to run or fixtures to run to get a traceback right there in your interactive developer console and a Python console. And there you see, okay, what is happening. So it's actually happening when get fitted params is being run. It's trying to access the self_forecast value when it's not set yet. Now, that's interesting because if you look at it, this is not misspelled. So, okay, it has the underscore at the start, but it's consistently wrong. So that can't be the problem. And if you look into the test, which I think can't do, or can I do this right here to print the test somehow? Yeah, I guess I can't do this because we don't have a clone, but you can just search, and what it will say is, this test trace is not fitted error, is testing if you call any of the non-state changing methods, like update, predict, or get fitted params is also on the list, and the estimator is not fitted, it should raise an error. And the problem is it does not, and not fitted error specifically, and the problem is it doesn't raise a not fitted error, it raises an attribute error. Right, so this one is relatively subtle, but once we understand that from the test, right, it's not 100% clear in the extension template, and as said, you might encounter occasionally that the extension template is not 100% clear, but that way you can still diagnose it, as I have shown you. So what you need to do is either that, or you could also do this, if not self is fitted. I mean, this is probably nicer if you do this, if you do it that way. Oops, so I cannot, this is a Mac. So you could also do this instead, and this is going to have the same effect. All right, so what this one's, it still has this old boilerplate, and there's only one piece of boilerplate for get fitted params, but it always needs to be there. So maybe if someone wants to make the first pull request to Sktime, perhaps these 2 lines should be in the extension template for get fitted params. As said, one example of imperfect documentation, you can track these things down by using 2 things, a check estimator traceback or the full test framework. Check estimator, use it with return exceptions equals false, and searching for the test and seeing what it does. All right, and along the way, we've also learned about the full extension template for forecasters. So some caveats, right? Again, if you follow the extension template, it's important to look for differences in signatures of public and private methods. Right, so private methods usually have a simpler interface, but this also means they have a different interface. So if you, for instance, have been using predict interval and you always just pass a number and you expect the private interface to have also a float for alpha instead of a list, then you might encounter an error. So it's usually well documented, hopefully in the doc strings of the private methods in the extension template, as well as in the base class, of course, which also has abstract versions of that, what these private methods are doing, what the contract is that you need to implement against. Another example, F8 is guaranteed to be a forecasting horizon, so if you always have been using lists or NumPy arrays, then you can't assume this anymore in the private method. You need to use the forecasting horizon, and the forecasting horizon is a central class which also has its own documentation. We won't go into details about it here. And the other example, obviously, and that's part benefit, partly a curse, that the y and the x are going to be in the specified formats in the x and the y inner M type. More and more about that below. Further, right, if you implement optional methods, a common mistake is that the capability tags have not been correctly set. So some tags, they're silent, some tags are only really there for findability, some control the behavior of the estimator, and check estimator usually will tell you if the tags are incorrect, but not always. Further, one minor detail. Right, so if you have an estimator, if you say in predict interval you want to call predict, it's usually better to call private methods from within private methods and not the public methods, because in the private methods the conversion has already been done. So let's say you want in your predict quantiles, you want to get the point prediction because that's the mean or the median of a distribution that you predict, then call self underscore predict from within self underscore predict interval and not self predict interval without the underscore, so self predict without the underscore from within self underscore predict interval. All right, next topic, tags. Tags and data types. So as an implementer, typically you can leave the tags as they are. They are sensible defaults. So the conversion tags for the internal data types, they will typically convert to something in pandas. So pandas with a specific additional assumptions, like for panel data having a row multi-index of instance and time, or for a single series just pandas series or pandas data frame. So these are typically set sensibly, but of course if you want to interface something, right, if you want to use Sktime as an interface layer, or let's say you need the data in a specific format internally, you should be aware how the tags work and how the data format, strings, and specifications work in Sktime. Generally, there's 3 high-level types of tags. So one type of tag tells you about the capability that the estimator has or doesn't have. That's very useful also for inspection. So the Sktime registry allows you to retrieve estimators allows you to tell the all estimators utility, okay, now find me all forecasters that can make a probabilistic prediction, for instance, or now find me all transformers that do something non-trivial with hierarchical data. The property and type tags, so they tell you about what inputs and outputs, so what inputs an estimator can handle, what outputs it produces. These are property, they are descriptions rather than instructions. And the final one is behavioral tags, so they are instructions, as in, for instance, inside the inner methods, so in underscore fit and so on, I want to see a NumPy array, I want to see a pandas data frame. So that tells the plumbing layer, I want you to convert my inputs to this and this or that, for example. There's some related methods that you should know. So get tags and get tag, we have seen them in the printout. That is called in the plumbing layer a lot. It can also be used for retrieval or property inspection of estimators. Say if you want to loop over the estimators and call probabilistic prediction only for those that can do probabilistic prediction. Now, as an implementer, you should also be aware of set tags and clone tags. So these are for developer use, and they're relatively rarely used by developers. I just want to mention them because, for instance, in composites, you may want to set tags dynamically in initialization. So, for instance, if you have a pipeline and you want to set the tag of the capability, can this deal with missing data? You may want to check that either everything in the pipeline can deal with missing data, or there is at some point an element that removes missing data. But typically, you will not use them if you implement estimators. Just good to be aware of. Now, examples, right? We've seen this already in the extension template. You run get tags, you get all the tags of a given estimator. And for forecasters, right, the behavioral tags are these four. So X inner M type, the two most important ones. What do you convert your data in the underscore methods? Then fit is empty, tells you so both in forecasters and transformers, is there anything in fit or do you want to skip it? And force index type is a check. It gives you an error message if the index of a pandas object is not of a certain type. It's rarely used because most estimators in Sktime actually do an index conversion instead of throwing an error message. Transformers have a bit more. The reason for that is that transformers are more polymorphic. So transformers can output, as we have seen, series. They can output a panel. They can output a set of scalars when you pass a series. So feature extraction from a series would output scalars. Most transformers for time series output a time series. So for instance, differencing or imputation, and some like bootstrapping or sliding windows, they even output the panel, and even also the inputs can be different. So due to this polymorphism, there are more tags which we need to control. Right? These are the property tags. So what's the input, what's the output? The instruction or behavioral tags, right? There's again the inner M types, and then two skip tags, so skipping fit or skipping inverse transform. So you see they're not entirely uniformly named, the tags, but of course it's a bit of a deprecation nightmare to get them more uniformly named. It will happen eventually. Okay, tags, to summarize, you have three types of tags: capability, property, behavioral. As an implementer, you need to primarily be wary of and care about the behavioral tags. And these X inner M type, Y inner M types, right, they are specifying a format specification, and that's a string. That's a string that refers to one of the specifications inside Sktime, namely to what I'm now going to explain in this section. So Sktime has a concept, a two-layered concept of in-memory specifications. Sktime aims to not have one specific format for time series, because we know that our users have different opinions about what the best input format is for time series and output format. And if you have collections of time series, it gets even more diverse. So instead, we collect specifications and support multiple specifications by wrapping or conversion. And that is done through the concept of Sci types and M types, or scientific types and machine types. Scientific types also are called sometimes abstract data types. So these are different conceptual types on the mathematical level. So is it a time series, so an object which collects observations indexed, time indexed, or any indexed 1D indexed observations. So it's the abstract data type behind the pandas series or pandas data frame. And also a NumPy 2D array could represent that abstract data type, although of course the interpretation of a 2D NumPy array is not clear. Whereas the M type, the machine type, or the concrete type is the specific representation that is being used for the abstract type. So example, a series with capital letters is a scientific type in Sktime, and a time series can be represented by a pandas data frame, by a pandas series, and a NumPy array with additional specifications. Those specifications you can read up in detail on the data types and data format specification part of the documentation. Now, for forecasting, for transformation, for time series, the three most important ones are series, panel, and hierarchical series. A single time series panel, a collection of time series, a flat collection, and hierarchical is a hierarchical collection of time series. So where hierarchies, where you can have more than one level of hierarchy. Examples for the panel. So for a single time series, the representation is relatively clear. For collections of time series, you have a lot of different data types. Some are preferences of certain communities associated with time series specific learning tasks. So for instance, if you do time series classification, you might like more the 3D NumPy representation or the nested pandas data frame representation, whereas if you do forecasting, you might find a row multi-indexed pandas data frame, a more natural representation of a collection of your time series. You can look up the explanation in the entire register of machine types and abstract data types in the data types module, M types register. So for the implementer, what is important to know is this string. Right? So if you enter this string, the M type string, in the Y inner M type tag, what you get? So what you get is a Y or an X that is compliant with the specification here on the right, or the more detailed specification in the data types and data conventions. So here's two examples: PD multi-index for a collection of time series. This is the PD multi-index M type. So columns are the variables, and the rows is a multi-index, two-level multi-index with instances and time points being the last one. They do not need to have specific names. The levels, the same collection of time series is also represented in this 3D NumPy array, and Sktime considers them as equivalent abstract objects. So you can use, for instance, also the convert to function to convert between the types, the representations, and this all happens automatically in the plumbing layer. So let's have a look at another advanced example. So let's say we want the min-max scalar to take the minimum and maximum across multiple time series, and not just for individual time series. So Sktime has automated vectorization for a panel and hierarchical data, so collections of time series. And that means what it will do is it will apply a transformer that is implemented only for a single time series to the individual time series. So the scaling will happen to individual time series. Let's say if we have this hierarchical data container and we apply the min-max scalar that we implemented So it has here values 456 and 455.6. In the first series here, it will scale the 4 to 0 and the 6 to 1, and the second, the 4 to 0 and the 55 to 1. But what we might want to do in this case, actually, we want to scale the 55 everywhere to 1 and the 4 everywhere to 0. Now, the default behavior is, as I've said, the scaling happens individually per time series instance. But if you want to have this happen overall, then you need to change something in the tags. So you need to, in the tags, in the X inner M type, you need to have at least a hierarchical data type. Yeah, so the one hierarchical machine type is this string. So it's the type in which this data container is. And if we look at the extension template, right, that means we need to fill in the X inner M type tag with a hierarchical M type, or preferably a list of M types which cover multiple scientific types. So we still want to work it for series, and we also want to work it to work for hierarchical data types. Now we are a bit short on time, so I just quickly show you the buggy version. So the buggy version is we just fill in the hierarchical M type. So we do that. It works as we intend for the hierarchical data container. It still works for single series, but in the tests it will fail if you pass, because if you pass the data frame, it will fail because we have assumed the series inside. So instead, you need to fill in a list, and if you fill in a list of M types, then it will search, is there something on the list which is of the same abstract type, so hierarchical or series, and then convert to, if the current M type is on the list, it will not convert. If something of the same psi type is in the list, it will convert to the first occurrence in the list. And in this case, we have put the machine types to cover the 3 time series, scientific type, series, panel, and hierarchical, and that no longer raises an error. So just skim over this, but you can, of course, look into the failure, and you can look into the example if you look at the notebooks. All right, so the explanation is, okay, we need to deal with 2 cases. It has a pandas multi-index, or it has a simple index. All right, last but not least, a composite estimator. So as in Scikit-Learn, you can pass estimators to the argument as an argument to the constructor. That makes the estimator a composite, also conceptually as recognized by, for instance, nested parameter inspection via getParams, which you might be familiar also from Scikit-Learn. We are fully compatible with Scikit-Learn there. So if you pass an Sktime or a Scikit-Learn estimator as an argument to a Sktime estimator, and it's a default, so it's by default always an estimator or none, then you will also get the nested parameter inspection from the getParams method. And what you need to look out for here, multiple things, right? Components should be passed to constructor, so you expect an object there, not a class. The object then should be written to self, again, parameter of the same name, attribute of the same name. You shouldn't fit the object that you pass. It needs to be considered as a blueprint conceptually. So you need to clone the object and fit the clone. Do not fit the argument of the constructor. Possibly you need to set dynamic tags if properties of the composite depend on properties of the components. You can leave that empty. For the descriptive tags, it won't make much of a difference. In methods, so usually you want to call the components methods from the composites methods. Always call the public methods of the component, not the private methods. So always interface the outer layer of the component from the inner methods of the composite. Finally, the non-state changing method should not call state changing methods of the component, because you do not want to change any state, not of the composite, not of components, in the non-state changing method, predict, transform, and others. All right, so let's have a look at composite moving average. And what we do here is, okay, we fit, so we give it another argument, the transformer. We fit the transformer on the data we see in fit, and after we forecast, we apply the transform of that transformer in the forecast. Right, so we write the transformer to self, okay. Then in fit, we fit the transformer on the data we all see, and in predict, here we add this line, we transform the prediction. Okay, all good or not? Well, the file is called buggy, so maybe there is some bug in here. We can ask again check estimator, and it says, oh no, the test fails, test fit does not override hyperparams. And what happens here, oh, the estimator should not change, and the parameter, so exponent transformer, that's in the get test params, okay, it's the transformer. So one of the examples, of course, needs to have a transformer that is not none, or of course we will not test the case where we have a component in there. And so we run the test, and in that case, that's the only case with a transformer that's not none. Oh, it's changing the state. And well, what did I just say? Right, we should clone the transformer. We should not fit the transformer we pass to the init. So this is a very common mistake, right? But it's also easily fixed by running clone. So you can run Scikit-Learn clone, or you can also run the any Sktime estimator has a method clone, which does the same thing. So you can do it either way. And then, of course, you fit. Oh, look, underscore at the end. Is anyone happy about underscore at the end? Yeah. And of course, you do what you do with the clone and not with the object you pass to init. All right. So now it works. Again, some caveats. Right. As I've already said, when you call methods of the components, use the public ones. Always clone components. Also important, it's quite subtle, don't overwrite conversion tags, the instruction tags of the components dynamically. It might seem appealing to do that, because then you avoid conversions sometimes. But if you do, then it invites a lot of pain, usually. So try to avoid conversions by, for instance, making your composite polymorphic. Right? You can pass a list of M types, and if you pass a list, then it's an OR. Right? If you want to pass NumPy and pandas, you just put them on a list instead of copying your component tags. And one very subtle thing in update, so even if you do nothing in update, you may still need to call the update of the components, because update does things like update the timestamp of the most recently seen data. And that's it about composites. Very quickly about test framework. So the easiest way, of course, is import check estimator and make it a part of your test. Important thing, you need to run it in the version that raises exceptions instead of returning the dictionary. Because only if it raises the exception, the test will fail, and it means setting the return exceptions flag to false. There's advanced way to integrate with your testing framework, including inheritance. You can read all about it in the developer documentation on the testing framework. I will not go into that in detail either. So, summary, Sktime is extensible, Scikit-Learn-like. You can build extension templates to build your own Sktime compatible components. There's a full testing integration with which you can use in your CI/CD. You can use check estimators, or, not shown today, inherit from the classes in the Sktime testing framework. And Sktime compatible components, even if they are in your own package, they will typically work out of the box with the Sktime framework machinery like pipelines and reduction. All right, that's it for the content. We have 5 minutes for questions. Maybe Leonidas, you want to come up here quickly. So as we've said, everyone can join. We have a developer sprint July 11 to 15. There's going to be a maintainer role advertised in the jobs channel. And we have a rolling basis mentoring program to which you can apply. We have currently Google Summer of Code running, and also a number of work streams you could join that are quite interesting. In the developer sprint, if you want to join that, here is a QR code that I'm now trying to display in a way that, oh no, there you go. Questions?
Do you have parallelization support for your pipelines that are implemented inside?
So some composites have job-lib parallelization support, some don't. It's inconsistent currently, and contributions on that front are obviously very much appreciated. Make a pull request, join a developer Slack, and help us making our pipelines more efficient.
Okay, thank you.
Everything has obviously been very clear.
If not, let's give a round of applause. Thank you.
So if you're not familiar with Sktime, you can watch the general tutorial. It's on YouTube, PyData Global 2021. Link is in the GitHub repository, as well as on the Sktime main repository. And if you want to join the developer sprint, it's here in London. Tickets are available July 11 to 15. Register online via Eventbrite. Thank you very much.
All right, we're going to take a 30-minute break, and then we'll start the next round. Thank you.